Welcome to section 3.2, number 12. For number 12, we're going to do a few things here. So let's read through the instructions. First, we're going to find critical numbers, if any, on the function. Then we're going to find open intervals on which the function is either increasing or decreasing and locate any relative extrema. Lastly, we're going to use a graphing calculator to confirm our results. So really what we're doing here is 1, 2, 3, and 4 things. To start with the first piece, finding our critical numbers, we're going to go ahead and take the derivative of our function. As you can see, the derivative of x squared plus 8x plus 10 is going to be f prime of x is equal to 2x plus 8. And this is a pretty simple derivative. Next thing is we'll take our derivative, we'll set that equal to 0, and we'll solve for x. So as you see, I've arrived at a value of x equals -4 for a critical value. And I'm sort of cheating on to using the graphing calculator and taking a look at my original function, x squared plus 8x plus 10. We know that this is a parabola, it opens up, and it has a vertex that has an x value of -4, hence our line of symmetry is at that point where the tangent line has a slope of 0 at x equals 4. And that's where we have some of our, or most of our critical values will be where the tangent line is 0, and of course if the function has any discontinuities. In an effort to drive the derivative concept all the way home, we take a look at our function f prime equal to 2x plus 8, and we notice that that function crosses over 0 at x equals -4, thus verifying again that our critical value is at x equals -4. So we can use the original function to look at that critical point, where is it making a turn, or we can look at the derivative function and see where it actually is crossing over the x-axis there for y equals 0. But let's move on. Our next charge was to find the open intervals on which the function was increasing or decreasing. Now as we take a look at the function on the calculator, we can see that we're decreasing from -infinity all the way down to -4, and from -4 all the way to positive infinity. Now that's analyzing this graphically, but we want to analyze this analytically as well. So using that value of x equals -4, we will write it as such. We have one critical value, so we're going to have two intervals, and that interval is going to come from all the way on the left, -infinity to -4, and then from -4 all the way to the right to positive infinity. Now that we know our intervals, we're going to have to come up with a test value, and then we're going to use that test value to figure out the sign of f prime of x at that moment, and this will help us figure out analytically what we already know to be true in the picture over here. So what I've done is I have substituted in some values, my test value of -5 into the derivative, and a test value of -3 into the derivative. And as you see over here on my scratch work, I have a y value of -2 when I substitute -5 in for x in the derivative. Thus my sign of f prime of x is negative on the first interval. And on the substitution of -3, I get a +2, so my sign of the derivative is positive. That being said, if my derivative has gone from negative to positive, then the function must have made a turn, therefore we have some relative extrema. If we're coming down, 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 and then going up, then we must have a relative minimum at x equals -4. Substituting in -4 into our original function would show us that at -4, -6 is our relative minimum location. So for a final answer expression, we'd want to lay it out like this. Hopefully that was easy enough to follow. Now you give it a shot. Take a moment, try number 16, as I have shown here on the screen. X to the third minus 6x squared plus 15 is the original function. Press pause now and answer the series of questions that we answered in the first example. Then press play when you're ready to check your work. Well, you know me, I like to do things a little backwards. I'm just taking a look at this graphically, and first I must apologize. I keep saying graphically and analytically. That is a total faux pas. We're talking graphically and algebraically. So looking at this thing graphically, I notice that we have a turn up here, we have a turn down here. We're continuous as a polynomial function from negative infinity all the way to positive infinity. So we're going to have two relative extrema, a relative max up here and a relative min down there. And also we're going to have three intervals, one here, one there, and a third one here. As we look at the derivative function, we notice that we're going to have two moments where we cross over 0, and that coincides with the concept of having two moments where we have a derivative equal to 0 in our picture, right? Our horizontal tangent line at those two moments. All right, let's get on with the algebra. First things first, we see that we have, after taking the derivative, setting the derivative equal to 0, two critical values at 0 and at 4. And that seems to make perfect sense at 0 and at 4. We'll take these critical values and set up our intervals, right, from that negative infinity all the way to 0, from 0 to 4, and then from 4 to positive infinity. I use those intervals to obtain a test value, and again, we want to make sure that this test value is a value that's inside that interval. So from negative 1 all the way to 0, I go with negative 1, because it's easy and cheesy, and a positive 1 for the 0 to 4. And from 4 to positive infinity, I go with 5. I substitute these test values into my derivative function, and I get a value for my first one. F prime of negative 1 yields me 15, which is positive. And as you'll notice, I substituted in 1, got negative 9, so that's going to be negative. And when I substitute in 5, I get positive 15, so that's going to be positive. So again, thinking about the fact that as we move from left to right, we're going from a positive to a negative. Between the change in between those two intervals indicates that we are at a local extrema. And then between the middle interval and the last interval, again, a change in that sign indicates a relative extrema. And now we're ready to present our final answers. All right, so we have a critical value, as we know, at x equals 0 and 4. The function is increasing from negative infinity all the way to 0. It's also increasing from 4 to infinity. It is decreasing from 0 to 4. We have a relative max up here at 0, 15, and I got that 15 value for f of 0 into the original function, right? 0 into our f function yielded us a answer of 15, or a height of 15, and a relative min. When we substitute 4 into our original function, we get a y value of negative 17. And that's it. You're ready to embark on a few problems on your own now. Good luck. Please bring to class completed with you numbers 14 and 20. For number 14, I would probably distribute the negative through before I try to evaluate the derivative. See you next class.